Welcome everybody. Thanks for joining us this evening. Finally getting a clear Friday night in Jackson, and we should be able to show you lots of cool stuff tonight. So yeah, throughout the night, Mike and I will bring up images, both pretty much live from his camera and telescope, and then we'll also show you some processed images that Mike's already done just to compare with the raw images that we take tonight. So feel free to ask all the questions you have about any of these objects throughout the evening, and we'll try to give you a bunch of information about them as we go. And so we're going to start, I think, with a couple galaxies to begin. I'm going to show you Bodes Galaxy, which is...
Yeah, so I'm actually taking a picture of it right now and see what it would. All right, well, it's much better than it was a few minutes ago because it was just a little too bright here. But I can see it, and I'll share my screen here in a second. Let's see. Okay, there it is. I'm going to minimize this. And let me work on the histogram a bit. Well, I don't know if you folks are able to see much here. Well, that's blowing out the center. Oh, yeah, you know what? I can...
blowing out the center, it reveals a little bit of the spiral arms. But
okay, I'm going to do a what's called a filter on this to which will. All right. Yeah.
Basically, the issue that we're having is that it's not quite totally dark yet. And so the contrast between the object that we're trying to photograph and the rest of the sky isn't quite good enough to bring out all the detail. But in the next few minutes, as it gets darker, that shouldn't be a problem.
Yeah, maybe maybe you even want to show a picture of this, one of my pictures, and then we can retake this picture because just minutes here will make a difference in the way this looks.
Yeah, definitely. Yeah, so
well, in fact, we could talk about this object too a little bit here too as well.
Sure. Let me bring up the image, and then we can share some information about it. I'll have it up in just a moment here.
How many light years away is this, Sam?
I think it's about 12. Isn't that right, Samuel?
This one is, yeah, I think somewhere between 12 and 12.5 million light years away.
Right.
Wow.
It's not in our local group. This is just outside our local group of galaxies. It's in the eastern sky at the moment, fairly high up. In fact,
so there you go. Hopefully you can all see that now. That's Bodes Galaxy, and in the next few minutes when we try to photograph it again, you'll definitely be able to see these spiral arms that you can see really vividly in this image.
Wow.
It's looking pretty good, Diane.
This is
and so what you're seeing here, this bright center is what was being blown out before in the image that Mike was trying to take. Recently, astronomers have pretty much nailed down that in the center of every major galaxy in the universe is a supermassive black hole. And you might think, well, I thought black holes didn't let off any light, so why isn't it really dark in the center of galaxy?
Right.
The answer to that is that there's huge amounts of material swirling around the black hole, giving off lots of light as it spirals in. And so that's why the center of these galaxies are so bright.
Yeah, there's just a concentration of just a tremendous number of stars in the center of the galaxy. And what you're seeing is the glow here. You're seeing the glow is the glow of all those stars, plus the ones, as Samuel was saying, that are right circulating close to the black hole itself. You can see in this picture, what shows up also nicely is all the, my pointer doesn't show, but all the red spots, Samuel, you can point them out. These are areas where hydrogen, gas is emitting light, and it's areas where there's a concentration of hydrogen gas. So these are star forming regions in the galaxy. And the stars, I should also say that the stars that you're looking at here are not in that galaxy. They're in our galaxy. They're in the Milky Way. They're just in front of the galaxy. So you can't actually, none of the stars that you're seeing here are in that galaxy. But the red spots, the red dots in this picture are in that galaxy. And they're huge, probably globular clusters of stars that are emitting that where the hydrogen gas is emitting that red light.
Yeah, but the points of light that Mike was talking about before, all these larger points of light, the ones that have crosses in them, those are the stars inside our galaxy, inside the Milky Way, in the foreground.
Right.
Even though they appear to be the same distance to this galaxy, they're much, much closer to us than the galaxy is. The stars are probably only hundreds or thousands of light years away versus the 12.5 million light years that this galaxy is away from us.
How much larger than our galaxy is this one?
This one's actually a little bit smaller than our galaxy.
Huh.
This one only has about 200 billion stars versus the estimated 400 billion that the Milky Way has. And in terms of overall size, I think this one is somewhere between 1/2 and 3/4 as long as our galaxy. Our galaxy extends about 100,000 light years across. If I'm remembering correctly, this one is somewhere between 50 to 75,000 light years across. So still big, just not quite as big. Mike, do you want to try to take another image?
I just did, yeah.
Okay.
Yeah, let me try it. I was trying it with the red filter, just seeing if it gave a better image. But let me do it again with the clear filter. I should say that the camera that is on this telescope is a camera that's designed to take long exposures of these deep space objects. It's not one you could use for taking pictures of planets, but it's a black and white camera, but you get the color, the way that picture, all that color information. Well, there it is. Okay, so it's better now. Let me share my screen, and you'll, I gotta find Zoom again here.
Yeah. So like Mike was just saying, this image that we're looking at here is taken through several different colored filters that Mike is then digitally combined to make this composite image. So when we see the raw image that Mike just took, what we're going to see is just black and white.
Yeah, and so where you get the color is, yeah, I take a picture through a clear filter, which is what we're doing right now. That's what this is. And then I take, and that provides what's called luminance, basically the brightness associated with the picture. And then you take pictures through the red, green, and blue filters, and you get the color information. And so you create a color image, and then you superimpose it on the luminance image, and that's how that other picture got created. In addition to that, I have 3 more filters on the camera. I have a hydrogen filter, an oxygen filter, and a sulfur filter that that are narrow band. They only allow light from a specific transition in those atoms, and it gives very detailed information about what's going on. For example, those red areas that really show up in that picture that you just were looking at were enhanced because I actually was taking pictures of that galaxy through the hydrogen filter, and I add that information to the color information that from the broadband RGB filters. And that's how that image got created. Now, the one you're looking at now is strictly through the luminance filter, but now you can see the arms.
We
were
can't
just
see it
looking
yet,
at.
Mike.
What's that?
We can't see it yet.
Can't quite see it? Okay.
Yeah. You
Let
got
me,
it. No, not the arms, but the image. Yeah, I think you need to do a new share.
I see. I thought, okay, I did. Okay, I'll stop share and let me do another share.
Well, I see this one in the paint program with a purple galaxy.
Yeah, Mike's trying to show you the one he just
You
took.
might have to stop sharing, Samuel.
Okay.
I think that's what happened is you're still sharing. You got to stop sharing.
There we go.
Okay. Yeah, I thought you could share over me, but I guess not.
No, no, not. So,
There we
okay,
go.
so there's a what's a 20-second image of this galaxy. That color picture was probably 10 hours of imaging.
Wow.
But this is a 20-second image. And you couldn't see, one of the nice things is by doing this virtual program is this galaxy, if you were looking at it through an eyepiece, you wouldn't see anything. I mean, you might see the center brightness, but you wouldn't see these arms. You know, if we might want to come back to this a little later. We'll get even better as time goes on. I mean, I took this picture, well, I just took it a few minutes ago, so it's not going to be any much different. We could also move on to the adjacent galaxy. There's another galaxy that's right next to this one. It's actually gravitationally bound to it. It's called M82. This is M81 in the Messier catalog. I'm going to stop my sharing on this screen, and I'm going to show you the screen that I use to actually control the telescope. And let's see, here we are. And I'm going to, come on, Zoom, where are you? Got to get rid of this. Find the Zoom window again. All right, Zoom, where are you?
So while Mike is doing that, so he mentioned that these two galaxies are gravitationally bound. So this next one we're going to see actually shares material with the one that we previously saw. And because of that, the spiral arms have been distorted. And this the second galaxy we're going to look at is what's called a starburst galaxy, not the candy, but the fact that it's undergoing a rampant amount of fusion of new stars. The new stars are popping into existence at a faster rate in this other galaxy because of the interaction it had with the one that we just saw. We think they swing past each other roughly once every 200 million years or so. Potentially they might merge together. We're not totally sure, but the effects are pretty easy to see in this other one, that they have indeed been interacting.
Sam, what would be the first clue? What would be the first clue?
Well, yeah, so I mean, the star forming regions that Mike mentioned before in this other galaxy, we see way more of them and much larger ones in this other galaxy. So that's one. The distorted shape was another giveaway in this other galaxy. And we should be able to actually see that shape once we get a picture of it.
Cool.
Yeah.
Yeah, my problem is now I'm screwed up with Zoom. Okay. I can't find the Zoom window.
Is there an icon down at the bottom of the screen?
Yeah, on my lower bar, the icon is there, but
if you click that, it should bring Zoom up to the front.
Yeah, it's not doing that. I mean, I can see you. I can see the image. Maybe I just have to. No. Okay, there we go. All right. I had minimized. I guess I minimized it, so I could see little images. All right, here we go. So so I'm going to share the screen. I'm going to go to this window here. Sorry about that. Okay, so what you're looking at here, I'm going to move this window over. What you're looking at here is a program called Skyx, and it's actually the program that controls the telescope. And so what we're looking at is an image, a graphic of the sky. And this is in particular where the telescope is pointing at right now. So, and I have it pointed at M81. So we're going to go to M82. I'm going to ask it to find it. It actually is right next to it. And in fact, my 6-inch telescope, I can actually get an image with them both in, because the 6-inch telescope is 1200 millimeters. This 20-inch is 3500 millimeters. So a factor of 3 difference in the field of view. So now I'm going to tell the telescope, I just said slew it. So now it has just moved imperceptible. You didn't probably notice the red dot moving, but it did. And now we're pointing at M82. And I'm going to now go to a different screen here. And I am going to take a picture of this object too. So here we go. So this is another 20-second picture of, but it's a smaller galaxy. It kind of has an interesting shape to it. It's got a very unglamorous name called the Cigar Galaxy. And there it is. I can probably, I'll go to medium here.
We can't see it, Mike.
Okay, of course I have to share again. Here we are. Thanks for reminding me on these small details. Okay, there we are.
Okay.
And let me zoom in a bit more. And let me try something here. I said I was going to try. Let's see, with I'm going to use a filter on this. Yeah. And how is that looking to you folks?
Pretty clear.
It's good.
Pretty good?
Yeah,
Okay. Yeah, so what I
shoot it
did
down
was
a little
I
bit.
used a filter on it that without the filter, I can show you, I'll undo the filter. It blows out the detail in the middle, but with this small, adding this small filter, you can actually see more detail in the image. And as Samuel was saying, this guy is actually robbing hydrogen gas from the previous galaxy. And in the if we showed you an actual picture of this, one of my pictures, you would see big clouds of red shooting on both sides of this, and just a tremendous amount of hydrogen emission caused by the stars in the area, exciting the hydrogen gas, and that's why it's called a Starburst Galaxy. So these are a pair, and yeah, this has it's called the Cigar Galaxy. I don't like the name particularly, but it is what it is.
Can we see one of the final prints to see the hydrogen?
Yeah, I'm working on bringing that up right now.
All right, I will stop. Well, leave this, and when you're ready, I'll stop sharing. Although I think your share can go over my share. Mine can't go over yours.
Yeah, I think so. Yeah, I just got to find this image really quick here. Let's see, M82. You know, Mike, I don't know if I have your picture of the Cigar Galaxy.
Okay, well, maybe you don't. And I don't think on this computer that I do either, so we're not going to get very far with it. Well, actually, that's not true.
I can bring one up really quickly. There are lots and lots of images of M82 available.
Now, I won't have it on my computer.
So Sam, can you look up images of everything in the Messier catalog, like in Wikipedia or?
Oh yeah.
Google.
We're all out there.
Yeah, I'll bring it up right now for you.
I have a way to do it.
Um,
While you're doing that, I'm going to do something here.
so that's the gas that Mike was talking about there.
Uh-huh.
Big clouds of hydrogen that have been stripped away from the other galaxy. And so this galaxy, we are seeing at a different angle, a different orientation compared to the last one. The other one was more face on, whereas this one we're seeing more edge on. And I'll bring up this other image. So here they are next to each
Oh.
other.
Cool.
Yeah. So the one we looked at previously and the one that Mike just imaged right now, the Cigar Galaxy.
But it is a spiral galaxy?
Yeah.
Seen in another plane?
Yep, they're both spiral galaxies, although the spiral arms in this one would be quite distorted if we had a top-down view of it. They probably wouldn't look as orderly as the spiral arms in this galaxy.
Uh-huh.
But we don't really know. There's no way to get on top of this one and get another view.
Yeah.
I don't know. That's good.
Yeah.
So is the hydrogen being sucked off by gravity?
Yeah, it's just a gravitational pull of that galaxy. Mhm.
Amazing.
Yeah.
Does
Like
it
I was saying
spin
earlier-
faster?
Oh, go ahead, Deborah.
Does it spin faster so it has more, oh, what's the physics term?
Angular momentum.
Inertial, say again?
Angular momentum. No, the
Yes.
the rotational speed wouldn't have anything to do with how much gas it's able to pull off the other galaxy. It's yeah, just a matter of how much stuff there is and what curvature of space it makes because of all its gravity.
So it's in essence a gravity issue.
Yeah.
Yeah. Mhm.
Well, Mike, should we move on to another object?
Sure. I was going to actually just take a quick picture of M81. I just moved it back to M81. But yeah, where would you like to go? Is there anything over on that side? I wonder if M51 is up high enough. We could take a look.
Yeah, let's
Because
give it a shot. That'll be real nice.
We are on the right. The telescope is on the right side of the mount right now for that. Once we go
Yes.
to the other side, it's
So what
Yes.
Mike is talking about is that we're right now we're looking at M82 and M81, so just off the top of the Big Dipper in Ursa Major, and we're talking about looking at this galaxy down at the other end of the Big Dipper. Although this chart right here is showing us where the objects are going to be at about 9 p.m. So at 7:30, it's quite a bit lower to the horizon, and it may be beyond the point where Mike's telescope can point. So he's checking that out right now, and if
Yeah,
we can go to it, this is an incredible face-on spiral galaxy. And if we can't do it now, we can definitely do it later in the evening.
Okay, so this is M81 again.
this is M81. Are you seeing it right now?
Yep.
In a second, yeah, there you go.
Yeah, this is M81. I've used a little magic on it to you can see the center. You can actually see some of the detail in the center now.
Yep.
Because I put a filter on and
Oh,
I'm
wow.
blowing it out a bit, but
That looks great right there.
Yeah.
yeah, you like that?
Yeah, just before
Just
that
like that.
filter, yeah.
Yeah, you can
Yeah.
see the
Yeah, we can see a lot of detail in the dust lanes.
yeah that you couldn't see before because it was blown out. Okay, let me stop this sharing here and go to back to my program, my Skyx, and let me just punch in M51 and see what happens.
Cool.
Turn off your video and your audio.
How's it look?
I don't think that's going to work.
No, still too low in the sky.
Well, there it is. Okay, M51. Let's see if a telescope will go for it. It's slowing slowly to it, actually.
Yeah, you want to bring up that screen so we can see it?
Yeah, I
moving
can.
up to it?
Let's see here. So now you see the yellow dot merging to the red dot.
Oh, yeah.
Let's see it. Yeah, and now it's there. Okay, so this is telling me it's 18 degrees above the horizon, so it's up there. It's up there. So I'm going to go and take a picture of it and just. I'll go to. Let's see.
This galaxy we're about to show you is twice as far away as the last ones we just showed you. So it comes in at about 25 million light years.
Wow.
And it's probably one of the most detailed galaxies you can see with even a relatively small telescope. With the telescopes that we use at Wyoming Stargazing that have 20-inch mirrors, you can actually see the spiral arms of this galaxy on a dark night. So we'll be able to make them out easy with Mike's telescope. There we go.
There you go. So that's the cigar on the right.
No. So this is a different galaxy.
Oh.
This is what's called the Whirlpool Galaxy.
Oh,
So,
yeah.
Yeah, so twice as far away as the last couple we just saw.
Wow.
But this is a large galaxy, roughly the size of the Milky Way. And it's got this little dwarf galaxy companion that it's gobbling up.
This guy, yeah.
And a little blob on the right there is eventually going to merge with the larger one.
Same physics.
So how is that? I've just done the filter on it, so it.
That's better.
Yeah, that's good, Mike.
Yeah.
Beautiful.
What the filter did, by the way, is it's called a nonlinear filter. It's boosting or reducing the brightness of the very brightest part of the image and maintaining the brightness of the dimmer part. So it's called the nonlinear filter, and you have to do that all the time when you're taking pictures of deep space objects, or most of the time, because that's the nature of the beast, that there's often areas that are extremely bright. That's particularly true on galaxies where the center is way brighter than the outer areas. And so all the pictures that Samuel has shown you, you use these nonlinear filters to try to dim down the bright part and brighten up the darker parts. In fact, the whole game in taking a picture of objects like this is you take the picture with as long exposure as you can, where you still get detail in the brightest part, and hopefully enough detail in the darker parts. But the way you get the detail in the darker parts is you just take lots of pictures, maybe as many as 100 pictures, and then stack them. You add them together, and the bright parts were already there, but then by stacking all the pictures on top of each other, essentially averaging, you reduce the noise, and you get a decent picture of the darker parts as well in the same image.
Yeah, so this galaxy is probably one of the most distant objects we're going to show you tonight at 25 million light years. To put that into figures that you can actually think about, each light year is 6 trillion miles. And we're talking about 25 million of those. So 150 million trillion miles. That's the distance to this galaxy.
And another way to think about it is the light that we're looking at here left that galaxy 25 million years ago.
All right. So
That doesn't blow your mind, nothing will.
Yeah. So that means we're seeing this galaxy as it existed 25 million years in the past. And there's really no way for us to know what it looks like today. Although 25 million years is really just a drop in the bucket for a galaxy. So, the stars have rotated around the center of the galaxy a little bit, but more or less, it's still the exact same galaxy that it was 25 million years ago. Give or take a few supernova and new stars forming.
So Sam, which telescope did we use to see this?
So Mike's got a 20-inch plane wave telescope at his house and a camera hooked up to it.
Yeah, I have 3 telescopes at my observatory. I have the 20-inch, I have a 12-inch, which is also a plane wave, 12 and a half actually, and I have a 6-inch, and they're all useful because they have different focal lengths, and you can take pictures of objects that are different sizes. I mean, you don't have a telephoto lens. The telescope is the lens, and so, for example, right now I'm taking a picture of something we'll look at, but I'm taking a picture of it with a 1200 millimeter lens, actually a 900 with the focal reducer, and it just gives you a really wide field of view. Whereas this object is quite small. It's about that the long dimension on this object is about 8 arc minutes, and that's about 1/4 of the size of a full moon. Now you could say, well, that's fairly big, but it's, as an object that amateurs like me can take a picture of and still get a good picture. This is one I can get a good image of. If Samuel will probably show you my image of this that I've taken. That's something like 60 hours of imaging to get the detail that they'll show you in a minute of what this one actually looks like. You see a lot more detail, but it's impressive that even a short exposure like this, you can the detail that you can see.
Mm-hmm.
Let me bring up that image that Mike is talking about right now, so you can see what it looks like when it has all of those hours of exposure.
So Sam, did we see that with the, oh, wow. Oh, did we see that with the Dobsonian only?
Yeah, we like I say, with our 20-inch Dobsonian scopes, the image that we can see with looking through the eyepiece is similar to what Mike just showed us in that raw image that he just took.
Right.
Not quite as well defined, but only on a totally moonless night. When the moon is out, the light from the moon brightens up the sky, and the contrast isn't high enough to see the spiral arms. But on a really dark night, we can see almost as much detail as the photograph that Mike took,
Wow.
the raw image, but nothing like this this process image. And what did you say, Mike? 60 hours of
60 hours on this one, yes.
Wow.
And the reason it takes that many hours is that you want to get an extremely high signal to noise. By probably over 200 images were taken to make this picture. And you, as I said, you take the way the picture is done, you take these luminance, just a clear lens, and you stack those, meaning you average them and you sum it up. Well, you don't sum it, you average it. Because if you summed it, the bright parts would get just brighter and brighter. So it's an averaging process. And what happens is when you average a lot of images, the noise gets reduced effectively. And so you get a higher signal to noise. So you create images from each of the filters, the red, green, and blue filters, and the clear filter. And by having 60 hours of the image, it means I can sharpen the image. I can bring the detail out, because if you don't have a really low noise image and you try to bring the detail out, all you do is just look at the detail and the noise. So the reason I can see so much detail, if you look carefully, particularly in the inner part of this inner part, you can see spiral arms very tight in that. And in fact, you zoom in on that, you'll see there's just a lot of detail in this image. And the only way I can get detail like that is by having 60 hours of imaging, and I use tools and software to bring out the detail.
So Mike, how do you know what the intervals should be between shots?
Well, what I do, the way the software worked, what way it was, that program that I was using to take these pictures, that program also has an automated aspect to it. And I don't have to manually take these pictures. I say I want to take, I think in this case, these are probably 10-minute exposures. And I say, take a 10-minute exposure through the clear lens, the clear filter, then another 10-minute exposure through the red, green, and blue. And then it just repeats it over and over again, as long as I can on any given night.
Right.
And then you just repeat the thing on night after night after night until you get 60 hours worth.
Wow.
And then you have a lot of fun with the software, doing all the stacking and everything else. And I tell people I enjoy all aspects of this. I enjoy taking the pictures, and I also enjoy the processing of them into an image like this.
Yeah, and so this is what you call a grand design spiral, with these kind of like perfectly symmetrical spiral arms that we see here. And not all galaxies have these, seemingly perfect spiral arms. Even the last one we looked at was a little distorted because of the interaction it's made with its companion galaxy. And not all galaxies have spiral arms at all. We think just around half of the galaxies in the universe have spiral arms. So of the 1 trillion galaxies that we think exist, 500 billion of them are spiral galaxies. The others include elliptical galaxies, irregular galaxies, peculiar galaxies, dwarf galaxies. So there's a whole zoo of different types of galaxies. None of them look quite as impressive, either as seen through an eyepiece or imaged as do the spiral galaxies. But there's a lot going on in the other galaxies as well. And I actually, I want to have Mike take a picture of one of the big elliptical galaxies in the sky for the next image. And we're not going to see a lot of detail because they're so bright in their centers compared to the outskirts of them. We're just going to see the very core of the galaxy. But the core of this in particular one that I'm going to have my photograph is special. It's Messier Object 87. And this was the big elliptical galaxy that just 2 years ago, the very first black hole was imaged. Not the black hole itself, but the accretion disk around the black hole.
Remember that.
By this gigantic telescope, or rather telescopes that were all linked together across the entire Earth, called the Event Horizon Telescope. And
radio telescopes.
Yeah, all radio telescopes, so not visible light. But they were actually able to image the accretion disk of the black hole in the middle of this next galaxy that we're going to show you.
Sam, how would you define accretion disk?
It's literally this flat pancake-shaped disk of material swirling around the black hole.
Okay.
And because the gravitational field of a black hole is so strong, this material is spinning around the black hole at nearly the speed of light.
Wow.
As it gets sucked in. So it's giving off a huge amount of energy and light. And so we can actually see that in radio wavelengths.
Wow.
So that's what this telescope imaged around that black hole. If you've seen the movie Interstellar, there's an incredible digital image of an accretion disk around the black hole featured in that movie. And they actually used real computer simulations to model what that accretion disk looks like. So when we actually develop telescopes good enough to see that much detail of an accretion disk around a black hole, it should look pretty similar to what we saw in Interstellar. Mike, let me know when you're ready to.
I'm ready, anytime.
All right, so I'm going to stop my share and then you can share your screen. And so I think a couple times Mike and I have mentioned the the catalog numbers of these objects as M or Messier. So Charles Messier was a French astronomer alive in the late 1700s, early 1800s, who was obsessed with finding comets. And I think he's credited with discovering somewhere around 11 comets over the course of his career. He also cataloged all the little fuzzy spots that he looked at through his telescope in the night sky that turned out not to be comets. And he knew they weren't comets because they weren't changing position night to night as he was looking at them. But he kept careful track of where all these objects were in the sky. And for him, they were the throwaway objects. It wasn't what he wanted to see. He had no idea what they were, just that they weren't comets. So he kept careful charts of where all these objects were. And today, Charles Messier is more well known for these objects that turned out not to be comets. So he'd be rolling over in his grave knowing that that's how we remembered him. But these group of objects include galaxies and nebulae and star clusters, and they represent 110 of the brightest fuzzy spots in the night sky. So every amateur astronomer in the world knows of the Messier catalog and the 110 Messier objects that are comprised within it. So we've seen Messier object 81, 82 already, and now we're going to go, oh, and 51. Now we're going to Messier object 87, this big elliptical galaxy with this black hole in the center of it.
Sam,
This isn't going to work out, Samuel. I just took a picture of it. It's only 6 degrees above the horizon right now.
Oh, no.
Yeah,
All right.
not going to happen.
All right, well, we'll come back to it.
So Sam, can you talk sometime tonight a little bit about the Webb?
Oh, the James Webb Space Telescope?
Yeah,
Sure. Yeah, we can do that at some point.
cool.
Yeah, I should mention this galaxy, the M87. Yeah, it's just too low in the sky, and 6 degrees. My telescope is not able to image that low. But as Samuel was talking about the spiral and the ellipticals, the spiral galaxies also are the younger ones, where the stars are grouped together in these bands. The ellipticals are often a result of a collision between various younger galaxies, and the spiral arms just get all messed up when that happens, and that they form this more amorphous shaped galaxy. So should we go to the other side of the world universe here and look at some things on the west side?
Yeah, that sounds great. Let's go to Orion, do the nebula.
Yeah, may as well just do that, because I'm sure it's dark enough now to see. So let me. This is going to take a little while because the telescope has got a ways to. It's going to flop, as they say. Maybe I'll.
Yeah, let's watch it do it.
I'll share it, and so you can watch it. Yeah. So
Sam, I have a question. You were talking about the Messier object.
Yeah, sure, Deborah, go for it.
So there's another seeming, I wanted to say cataloging, NCG.
Yeah, new galactic catalog.
Yeah,
there's
so,
a ton of different catalogs.
Yeah.
so what's the what? What's the difference? What's the,
Oh,
is
so,
the ends-
so the Messier catalog are just the 110 objects that we think that Charles Messier observed.
Yeah.
And as Mike just mentioned, there are several other catalogs that are more what professional astronomers use to categorize objects. So the new galactic catalog is one of them, and it has thousands and thousands of galaxies in it.
Yeah, every object that's in every Messier object also has a NGC designation as well.
uh-huh.
In fact, the one we're going to now is Messier 42. You can see it in the screen. Is my screen looking visible?
Yeah, we can see it, Mike. Yeah.
Okay, so you can see the telescope is swinging around. It's now pointing right now. It is now pointing at our North Pole, our polar axis, and now it's swinging down and executing this what is called a flop. The nature of this mount. And this object is 1976. It's NGC 1976. The designation, if you want to know what that catalog number is. There's also an IC, we'll actually look at an object in the same constellation that has, it's called IC32, which is Integrated Catalog, IC. So there's just a lot of different, there's a Caldwell catalog, quite a few different catalogs. All right, so we're now just about there, and it is now, the telescope is now pointing right now. See, it just said now tracking, so it was slowing, and now it's tracking. Now I'm going to change the screen and go to the screen where we take pictures with, and I'll share that.
So we're about to look at an object back inside the Milky Way galaxy. So far, we've just seen galaxies beyond ours. But this next object is the Great Orion Nebula. And I think we've actually mentioned this type of object a couple times already as these big clouds where star formation is happening that we could see in the spiral arms of those previous galaxies we looked at. This is a star forming region within the Milky Way, and probably one of the most famous star forming regions because it's so bright. You just need a tiny telescope to be able to see this object. And it's part of a really prominent constellation in the winter sky, Orion. So it's just down below Orion's belt in Orion's sword. And we're just looking at the very center of this nebulae. It's massive. I believe it's about 75 times the diameter of the solar system.
Wow.
And so a huge cloud of hydrogen gas and trace amounts of other elements where pockets of the gas have become so hot and so dense that new stars are forming. And these stars that are forming, they're already seeded with all of the heavy elements necessary to form planets. There we go.
Wow.
Lovely. Just like our sun. And so the Hubble Space Telescope can actually see planets or planetary disks forming around the stars inside this nebula.
Cool.
Now, this is one of the most famous objects in the sky. For one thing, you can actually see it, not with this detail, of course, but you can actually see it with your eye. It looks like a fuzzy, just a fuzzy area in the sky, as Samuel was saying, in the sort of right in the lower triangle, the lower half of the Orion constellation. If you look sort of right in the middle of the lower part of it, that's where this is. And let's see, if I change the brightness of this with the histogram, we might be able to see, well, darken.
Pretty great right now.
Yeah, I was just seeing if we could see the yeah, that's a nice image right here.
Yeah.
You can see these clouds. These are all, most of this is hydrogen gas that's being emitted by the bright stars. The stars in this area are tremendously bright. They're very young stars, and they emit a lot of UV radiation that's causing the hydrogen gas and oxygen gas in this nebula to emit light. And but so most of what we're looking at is, and so this is actually called an emission nebula, where the light is absorbed by the hydrogen gas from the stars, and then it is re-emitted to see the patterns you're seeing here. You can also see there are other sections of it that are dark, like this is just an area of dark gas that's not emitting light, it's just blocking light.
And is there dust in there as well, or is it just pure gas?
No, it's dust. That's what I mean when I meant this dark area. That's what that is. It's essentially dust. It's essentially dust.
Gotcha.
And it's not emitting light, it's just blocking light.
Right.
Yeah, and think about the quantity of dust necessary to make planets like Earth, Mercury, Venus, Mars. That's the amount of dust that we're talking about within this nebula. Not just for one new planetary system, but for hundreds.
Wow.
So there's a lot of dust. It turns out that typically when you find huge gas clouds like this, you also find a lot of dust.
And what is the dust?
It's literally the leftover remains of previous stars that have fused those elements in their cores and then
Mhm.
either wafted those elements out into space or exploded violently as supernovae. So
So they're generally heavier elements?
yeah, I mean, basically everything on the periodic table can be found in some trace amounts within this cloud.
Well, you know, you think about dirt, it's just combinations of elements forming various compounds that are inert, and they don't interact with light, they just block it. It's just,
Right.
it's nothing magic. It's just, but as Samuel was saying, there are some of these, there's certainly iron and magnesium and all the elements that are present forming compounds that are just do not interact with light, and so they just block the light and form dust. And there are some galaxies, there are some nebula. I'm not sure we'll actually look at any tonight. Most of the ones we're going to look at are emission nebulas, but that are considered reflection or nebulas. And there are some areas that they're called coal sack, which is just an area where you don't even see any stars. The stars are all blocked out, and you see a shape associated with just the lack of stars.
Wow.
It's called a coal sack or something to that effect. But in this image, you can see the effect. I mean, this area in the center, Samuel can point it out. Well, no, I can. You're looking at my image now, so my pointer works. So this area here is essentially some of this dust that's just blocking the light from this area behind it, which is extremely bright. And what I did was I used this filter. If I undo the filter, you can see how things change dramatically. So that's the image that we were. So the filter is actually quite nice, providing you can see a little more of the detail in the outer areas in particular, and see some of the detail. These three stars here are very conspicuous. You can see those three stars if you're looking at this through an eyepiece. You can see what's called the Trapezium Stars, and I can just barely make them out right here.
Yeah.
I was thinking if I can dim this some, I can might be able to. Well, but these three stars, all these stars are very visible through an eyepiece. This is so bright that a lot of this is this is really one of the really beautiful things to look at in real time optically through an eyepiece.
Yeah, you get to see a little bit of a green color when you look at it through the eyepiece of a telescope. But when you take images through a telescope like Mike's through different color filters and process those images, you eventually end up with something much more dramatic, which I want to show you here.
What can you tell us about the nebula to the left?
The smaller one on the left?
Yes.
This guy here?
Yep.
Yeah, that almost looks like a turkey's head, doesn't it? That's what I think of it as. This almost looks like a turkey in some ways, with the feathers and yeah.
Mike, do you know if these two are actually physically associated, or are they just lined up along our line of sight?
No, they're all. It's all part of the same basic cloud, yeah.
So part of the same complex, part of the same star forming region. So right in the center here, I don't think we can quite see it in this image either, but there's this area called the trapezium where there are 4 stars that we think are some of the youngest stars in the Milky Way that we can see, only about 10,000 years old, which for an object that exists billions of years is really just a few seconds old. So they really are baby stars that we can see forming out of this cloud.
That is so cool.
See, I'm actually dimming the outer areas and trying to bring out the detail in this.
Hey, Mike, by the way, when are you going to have your next display at the library?
The next what?
Display of your photographs?
Oh, display. Yeah, that's an interesting question. In fact, some of you may have seen it last year. I had a display in February and March, but it didn't stay up very well. It actually stayed up all through the time when the library was closed, but because it was blocked out for most of its time, it's going to be redone, and I'm going to put it up again.
Great.
Exactly when, but it'll be sometime within the next year, I would guess.
Awesome.
Yeah, if now I can let me zoom in here a little bit now too. The other way around.
How far away is this galaxy?
It's about
Nebula.
5,000 light years.
5,000.
Yeah, much
Yeah, so-
closer than anything
we-
we were looking at earlier.
Yeah, I mean, this is like in our close stellar neighborhood compared to the stuff we saw before.
Yeah, if you look carefully in the center here, you'll see 4 stars, or there's at least 1, 2, 3, 4. That's part of what's in the trapezium, and these are extremely bright stars that are very young. Okay, so you want to? I'll stop sharing. Well, you can share on top of this one anyway.
Yeah, but let's go to another object.
Okay, you want to? Since we're so close, shall we go to the? I think we'll
Horsehead?
see.
Yeah,
the
let's do
Horsehead.
it.
Yeah.
Yeah.
Okay.
Yeah, so there's another treat in this part of the sky, actually part of the same big complex of hydrogen gas called the Horsehead Nebula. Definitely one of the sought after things for amateur astronomers to see, actually just looking through a telescope. I've never been able to find it myself, but apparently you can actually see this next object that Mike's going to photograph just by looking through the eyepiece of a telescope, but it's really small. So photographing it makes it quite a bit easier to see. And it's got a cool shape to it. That's where it gets its name, the Horsehead Nebula. And so Mike will get an image of this for us in a sec and bring it up.
Okay, I moved the telescope, and it's very close. This is very close to one of the belt stars, the leftmost belt star in the Orion belt.
And so, Mike, is the Horsehead Nebula technically a dark nebula, or is it also emission?
It's both, but the Horsehead itself, that's a good point. The Horsehead itself is a dark nebula, and it is blocking the light from the. Let's do this.
There we go. Now I see it.
There it is.
Yeah, might have to bring out the contrast a little bit more.
Yeah. Brighten it up. Let me do let's do this on our high. Yeah. Okay, let's try the filter will help this or not.
A little bit.
Yeah.
That's clear enough to see.
So that's good. Yeah, that was good. What you just did there.
Is that better?
Yeah, that's great.
Okay. Yeah, so that's the Horsehead, and you can see the shape. There's it kind of looks like a horsehead. A friend of mine, Martin Murphy, said actually what this looks like to him is a headless skier, or a skier with it, because he's got an arm here and he's got an arm here and his body here, and he's skiing.
Oh yeah, you can see that.
Yeah. Yeah, so this is and this is another area here that's actually part of the emission. So what's actually going on here is that you can see the light in the background here. This light is coming from hydrogen gas, so it's emitting. The stars in the area are emitting the UV light, exciting the hydrogen gas, and it's emitting it. This cloud, this is really black dust. This is what we were talking about earlier. It's a cloud of dark dust, and it's just blocking the light. So it's a silhouette, essentially. And the leftmost, the Alnitak, which is the name of the leftmost belt star, is just off to the left part of this image. In the image I'm taking with my 6-inch telescope as we speak here, all of that is shown. It shows this, and there's another a nice feature in this image, off to the side. Is called the Flame Nebula. And so with the 6-inch telescope, I'll have a picture of the Horsehead, not so much detail, but with the Horsehead, this nice little feature down here, as well as the Flame Nebula and the entire expanse of the hydrogen emission, which is quite spectacular. I think, Samuel, you could actually show a picture of that, and you can see what
Of the
what
Flame Nebula?
well, of the whole. I think you probably have a picture of the Horsehead taken with the 6-inch telescope that kind of shows the whole area around here.
Yeah, I think I do. I will bring that up in just a moment for folks.
Yeah.
Yeah, here we go. Oh yeah, and you can definitely see the whole thing here. Yeah. All right, I will share my screen and show you that object. There you go.
Oh, wow.
So there's that little Horsehead that we were just looking at, and the Flame Nebula that Mike just referenced.
That's with how many filters?
Yeah, so this is actually taken with the narrowband atomic filters. So this is letting the light only through this filter that's coming from the hydrogen emission. So that's what all this red, but this is in the hydrogen emission is in the red. So this, while this is called a false color picture, false color image, hydrogen is in the red. So this is fairly representative of what the color actually is. But you can see these clouds, and so all of this is just hydrogen, massive hydrogen gas that's emitting, re-emitting the light. This is the leftmost star in the belt, right there.
Yeah, so we're looking right into Orion's belt. And to put this in perspective to size, the Horsehead here, that's about 3.5 light years. So just shy of 20 trillion miles. Just that little head right there. Yeah, 20 trillion miles right there. Our entire solar system, to put it in comparison, is about 1 light year if you take it out to the extent of the Oort cloud, the spherical shell of comets that's believed to encircle the solar system. So you could stack 3 of our solar systems end to end in the Horsehead Nebula right there.
Wow.
This is a huge complex of gas.
Yeah, the whole Orion constellation has something what's called the Orion molecular cloud, and this is just a part of it. And there's a lot of hydrogen gas and oxygen. There are some of the you'll notice there's blue color in this as well, because in addition to taking the picture through the atomic hydrogen filter, I also am using a oxygen filter. And oxygen is also, and this is a false color image, but it's fairly, again, close because oxygen is in the blue-green part of the wavelength. And so what we're seeing is this purple color is due to the mix of the hydrogen gas emission and the oxygen gas emission.
Single dual band filter?
What's that now?
Is this taken through a so-called dual band filter or two?
No, it's a single band filter. There's 2 separate filters, so it's a combination of images taken through the hydrogen filter alone, and then through the oxygen filter alone, and then combined in a color image where both the red and the blue color is showing. So this is yeah, I made a color picture from the 2 from each of the filters.
Understood. Does anybody know the name of the large bubble shape or arc structure that we see?
Are you talking about this one here, or the entirety of it?
Yeah, the big arc over the entire, almost the entire frame. It's almost like a bubble over the entire structure.
Yeah, it is. And it's
I
quite
don't-
spectacular, isn't it?
I don't know if it has a common name.
Well, I don't know about a common name. I meant
No,
IC
it's,
or NGC or anything. Or or LBN Nebula number or
Yeah,
anything.
I don't know what the designation is, but there is an NGC designation for this as well. I guarantee there is. I just don't know what it is.
The
Yeah,
reason I ask is because I've looked.
Yeah,
Yeah, we'll look it up and figure it out.
yeah.
I appreciate it because I've
Yeah,
tried
there's
to find
another,
it.
there's an NGC designation for the Flame Nebula too, again, which I don't have memorized. This particular image, and the way I got to it with my telescope is I used the designation IC, Integrated Catalog 434. So that's the catalog number for this object alone. And when you, of course, if you do it with a telescope that has a big field of view, you get the whole scene here, which is really quite spectacular.
Forgive me, but IC stands for Index Catalog.
Okay, sorry about that.
Yeah, they were both done by Dwyer back in the last century.
Okay.
Although I don't remember which century that was the 1900s, 2000s.
Fair enough. Mike, I was thinking we would show everybody a different type of nebula now. There's a
Okay.
prominent planetary nebula.
Yes. Okay.
Messier 93, just outside of Ursa Major, the Owl Nebula.
Okay. I haven't actually imaged that ever, so that'll be interesting.
It's pretty
so
similar to the Ring Nebula in brightness, maybe a little bit fainter.
Okay.
I'm sorry, forgive me, it's 97.
97. Thank you. Not 93.
Who,
You gotta
who
show
is
up more
who-
often, Mark, and keep us in line.
who is actually speaking here?
That's Mark Christensen.
Okay, great. Well, it's good there's someone keeping us honest.
Sitting under cloudy skies in St. Charles after 4 nights of imaging.
Oh,
It's all right.
yeah.
Okay, so I'm going to, why don't you stop sharing this? And I am going to get to my, so we're going to, what do we say, Messier 97?
97, yep.
Sam, can we see the Horsehead with your Dobsonian?
I've tried, Benj. I have never been able to find it, but
Let's try again.
according to other amateur astronomers, we should be able to.
Oh,
Okay, this
man.
is going to cause the telescope to flop again. Is there anything we want to see on this side, do you think, Samuel?
Let's take a look. Over by Orion. Oh, you know what? Let's take a look at the Crab Nebula, M1.
Oh,
Yeah, we could, yeah, absolutely. Yeah, that's
Do it.
that's close by. So
Yeah, that's a good one.
the other one I was thinking of is the Rosette. I don't know how that would look in a
Yeah,
short
the Crab
exposure.
Nebula should be quite nice.
Yeah, Crab will be nice. M1. Yeah,
And
that's
then we
right.
can,
That's right next door. So
yeah. So we're going to look at a different type of object, another type of nebula, actually. This one is a supernova remnant. So the leftover stuff from an exploded star. And one of the really interesting things about this particular supernova remnant is that we think we know when the star actually exploded. We think it exploded in the year 1054.
Oh,
And the
wow.
reason we know that is because careful records were kept by Chinese astronomers.
Wow.
And they called it the guest star. So this new bright point of light appeared in the sky and then probably faded away over the next several months or potentially as much as a year. We think that that corresponds to this, this fuzzy spot in the sky that we can see with even small telescopes. There it is there. Mike's got an image of it for us. The other really dramatic thing about this object is that over the past 50 years of imaging it, we can actually see the gas continually expanding away from its center. And so there's some amazing time-lapse images that you can look at online of this object getting bigger and bigger over the past 50 years as the gas is expanding outwards away from the spot where the star exploded.
You said that was 1041?
1054 AD.
Oh.
Yeah, 1054. And so when big stars like this explode, stars that are much, much larger than our sun, at least 5 times as massive as the sun, they go big in what's called a supernova, where the majority of the star gets torn apart and expelled out into space, except for the core of the star. A couple different things can happen to the core of a star after the supernova event. The core can stabilize into a neutron star, or it could potentially collapse in on itself and become a black hole.
There is a neutron star in the middle of this one.
Yeah, and in this case, we think it's a neutron star, and actually a spinning neutron star that we call a pulsar.
Yeah.
We won't be able to see the evidence of that with this image, but Mike, do you want to zoom in a little bit so we can see some more detail?
Yeah. So, yeah, a remnant of a star that was not quite big enough to form a black hole, but formed but did supernova and created a neutron star, which is some of the most dense matter known in existence.
Yeah, so to kind of put that into perspective in terms of the density of the star, the dead core of the star, the pulsar that lurks in the center of this cloud of gas, a few tablespoons of that would weigh several thousand tons.
Oh my God.
It is really dense material. If you think about the classical model of an atom with the nucleus in the center and electrons moving around that quite a ways away from the center, in a neutron star, all of that space is full of neutrons, of nucleus. So it's the densest stuff that we think can exist before you get something as dense as what's necessary to form a black hole. And the cores of these stars are small. They're the size of cities, but with pretty incredible density.
I'm trying to think also of another object that we've looked at, but I forgot the designation. We looked at the Bubble Nebula.
Yeah.
Yeah, what is that? You could look it up on the web.
Sure.
There's also the Rosette.
Yeah, I still think the Owl Nebula would be cool to see as a.
Okay, well, that's one's on the other side. So why don't we end with that one?
Okay.
Because that's going to cause me to move these objects. I don't know. I know the Rosette is not far away from where we are right now.
Yeah, the bubble is over on the other side of the sky.
Yeah, also we could look at both of those. Maybe that's what we'll do is look up the Rosette. What I'm curious what that might look like.
Don't forget about M78. It's right nearby where you're looking in Orion.
That's right. Yeah, it is, and I have a nice picture of M78. We could quickly look at that one.
Rosette is in Monoceros.
Yeah, it's very close also.
Yeah, whichever one you'd like, Mike. I'm game.
Well, what do you know what's the designation for the Rosette?
The Rosette is NGC 2244.
2244. Okay. Let me just quickly go to. We can take a quick look at M78. M78 is not an emission nebula, and so that's a different classification. It's a reflection nebula.
Mm-hmm.
Okay, we're there. Take a picture of it.
Is this the Owl?
No, this is a different type of nebula in the Orion constellation.
Oh, it's in the
Um,
Orion. Okay.
Still a different type of nebula than what we've looked at before.
It's known as the cave.
Thank you.
What do you think, Mike?
There it is. Not all that interesting, but it in a composite image taken over a long period of time is really quite beautiful. I can let me share my screen here. There it is.
Hmm.
Not quite as interesting as the Orion Nebula or the Horsehead.
What's the name
Did
again?
you already do that digital filter to it?
I don't know that I was told it's called the cave. I'm not sure that's right, but it might be. Let's try 2244. You said, right? I think
That's the Rosette Nebula.
that's the Rosette. The Rosette is a beautiful nebula. I'm just kind of curious myself how it looks would look like in a short exposure. It again is very close to where we are, so it doesn't take the telescope long to get there. It's just
Sam, did you say the Rosette is NGC 2264?
2244.
44.
yeah, I have some nice, very nice pictures of the Rosette. It's one of the spectacular images to take in the winter sky because it looks like a flower. That's the designation.
Yeah, I've got one of those pulled up if
Yeah.
once we look at the real one.
All right, let's see. I gotta go.
Uh-huh.
Well, they're not. They're not very interesting, I don't think. Let's see here. Hi. I can see barely. I can see a little bit of it. Let's see if I can get it to. Oh, there. Well, there's something. All right. It's since we're here. We'll take a look at it. It's maybe I can. Let's try a longer exposure, and I'm gonna do it with a 6.
Electron.
I'm going to do a 30-second exposure on this. This is interesting too because it has a beautiful star cluster in the middle of it. In the hole, the Rosette is looks like a flower with a hole in the middle of it, where you might find the petal, the nucleus of this flower, and right in that is a. Okay. All right, well, I was seeing something here. I'll just make it a little brighter. Okay, I have to share my screen though.
Yeah. Oh yeah, you can see it there.
Very cool.
Yeah.
Yeah.
Now that'd be a good one with your 6-inch.
Yeah, well, this one is actually a pretty good one with my 20-inch too. I've taken it both ways, and but you're right. This one works best with the 6-inch. But you can see the center here is a cluster, and if I put this filter on it, it's yeah, maybe do it at 50%.
Mm-hmm.
So you can see some of the shapes here, the dark areas in the petal, outer petal, and this is the center area, which has this cluster, open star cluster.
I'll if you want, Mike, I can bring up one of your processed images of it.
Oh yeah, may as well. Yeah, I'm going to save this one just because.
A friend of mine used to call that the landing lights cluster.
Landing
Nice.
lights,
Yeah,
I like
because
it.
of these stars here.
yeah, they form two lines.
Yeah.
Oh,
Yeah.
yeah.
Oh, I see, here, here,
Yeah.
this, and this.
Yeah, it's not an official name, but none of those names are anyway, so.
Yeah.
No, yeah,
All right, I'll bring up your image of it, Mike.
all right.
There you go.
Oh, wow.
This is in the Hubble palette, right?
Yes, this is in the Hubble palette. So this is, you can see what we were just looking at was, we saw a little bit of this. We were looking at this section right here with the 20-inch, but this was taken with my 6-inch telescope. And yeah, it's in the Hubble palette. So what that means, Hubble's narrowband images, when they're using atomic filters, they assign hydrogen, which has as green. They assign sulfur, which is a slightly longer wavelength, as red. So they in a progression. So sulfur is red, and that's what you're seeing on the outer areas of this. There's this reddish color, and then the blue is oxygen. So this is a 3-color false color image. With the red color is sulfur, the green color is hydrogen gas emission, and the blue is oxygen gas emission.
So then what are
Okay.
the wormy looking things?
Those are, that's dust obscuring the
Okay.
light from the gas behind it.
Cool.
And you can see why it's called the rosette. I mean, it does look like a flower.
Mhm.
Well, Mike, we just have a couple more minutes before 8:30.
Yeah, and so shall we flip over to the other side and take a look at some?
Yeah,
Okay,
yeah. I think the Owl Nebula will actually be quite nice.
okay,
Well,
so we'll do that next.
Hi, Sharon, you can show folks the telescope doing the flop over there.
Yeah, we'll do another flop here. So here, I'll share my screen again. Okay, so here's the all right, so here's where we are, and now I'm going to designate. Again, that was M97.
Correct.
M97.
Thanks to Mark. Otherwise, we would have
Yeah.
been looking someplace else in the sky.
Okay, so there it is. The red is on the other side. I know it's on the other side because it's purple color. I could go without flopping the telescope anywhere from the purple to the red, any place from here over, but that's on the other side. And so the telescope, as soon as I tell the telescope to go there, it's going to go on this flopping maneuver where it's going to trace a path up through the polar axis, essentially go right through Polaris here. And I could speed the telescope up a bit. I'm using a different program, a different computer here, and I haven't gotten everything sorted out. So it's moving, the telescope is moving quite deliberately here.
As long as we don't bump into another telescope, I'll be happy.
Yeah, that's right. The other one is pointing, yeah. That has happened. These two telescopes don't tend to run into each other very often, fortunately.
Is the Owl Nebula in the Messier?
The Owl Nebula is a Messier. Yeah, it's M97.
Oh, this is 97. That's right.
Yeah. The only thing is that it's not as bright as the Ring Nebula. And the Ring Nebula is like, it's so good of an example to show people of a planetary nebula. We usually don't do this one a lot, but the Ring Nebula isn't up this time of year.
Right.
So this is the next best thing.
Yeah, a lot of nice
especially
stuff
for a
is up.
planetary.
Just wait till 5 in the morning.
There you go. Yeah, you just have to stay up a little bit later. So a planetary nebula, it's got a horrible name because it has nothing to do with planets. So about 100 years ago, when astronomers were first finding these objects, they were these circular shaped clouds out in space. And astronomers thought that they might be planets taking form. We now know that they're sun-like stars that have run out of fuel. And so our sun, when it runs out of fuel, in 3.5 to 4.5 billion years, will become one of these planetary nebula. Stars like our sun don't have the mass to go big at the end in a supernova. They kind of die with a whimper and just expel their outer layers out into space. They become quite beautiful clouds of gas in doing so, and destroying the planets as the sun will do in 3.5 to 4.5 billion years from now. But nonetheless, we'll look a lot like this object after the sun expels its outer layers and becomes a planetary nebula. There we go.
Oh, yeah. We've seen this, right?
Well, the Ring Nebula is really similar, but this one's a little bit different. This is the Owl Nebula, but yes, same shape, except the orientation is a little bit different. So we're not looking straight down through one end of the nebula, but kind of off to an angle.
Okay.
And so instead of there being a neutron star or a pulsar in the center of this object, there's a white dwarf star. And that will be the fate of our sun as well.
Yeah, the white dwarf is actually a very dense star too, not nearly as dense as a neutron star, but it is packing electrons at the maximum density. You can actually pack electrons, and so it is a very dense star as well.
And so
it is not actually emitting. It's not. There's no nuclear reactions going on there either. It's just essentially an ember, and it will eventually cool off and disappear. But it does look like a star though, but it's not actually emitting. It's not. There's no nuclear reactions going on in it though.
Sam, would you repeat what the sun will fade into again?
So eventually the core of the sun will become a white dwarf.
White dwarf, thank you.
Which is the same core that's in the center of this object. But the outer layers of the sun will then expand outwards past the orbits of the outer planets and become a planetary nebula.
Okay.
And it'll probably become roughly the same size as this object. So this object is about 1 light year in diameter, about 6 trillion miles across. And that's probably eventually how big the expanding gas cloud of the sun will be, which means that expanding gas cloud will have ripped through all the planets of the solar system, potentially, not destroying the cores of the inner rocky planets, but probably destroying the outer atmospheres of all the big gas giants. Although interestingly, we have now identified a few white dwarf stars with big gas giant planets around them. And the big question is that astronomers haven't answered yet is that, did those gas giant planets actually form after the star became a white dwarf or before, and the expanding gas of the white dwarf just didn't destroy those outer gas giant planets? We don't know yet.
Oh.
But the reason this one's called the Owl Nebula is that it's got those two kind of dark marks near the center, which somebody thought looked like the eyes of an owl.
Okay.
Okay.
Well, it's about 8:30 in Wyoming, and so we were supposed to wrap up around now. I really still want to see if we can go to M87 to see if it's above the horizon. It's not a magnificently looking object, but it is kind of cool to be staring into the part of a sky where a supermassive black hole resides. That might be a fun grand finale if it's high enough now, Mike.
Okay, we can take a quick look at it and see.
And if not, we can just end it here. But as Mike is going to that object, I just want to say thanks to everyone for joining us tonight. Really nice to see so many people being here for the first virtual stargazing we've been able to do in a while. Hopefully, as we move into the spring and the summer, we'll have more and more clear Friday nights, and we're able to do more of these programs. And if there are any objects that that you really love in the night sky, that you'd like us to take a look at in upcoming virtual stargazing programs, you can send us your requests and we'll queue them up for you. You can send those requests to info@wyomingstargazing.org or to samuel@wyomingstargazing.org, and we'll put those objects on the list for you. So there it is. We've
Okay,
got
well,
it.
there it is. Yeah,
Yeah.
it's yeah. Let's see if I do my filter and see what happens with that. Well, that that doesn't do much for it. So
Spins it out. Yeah. So
yeah.
what we're looking at here is the core of a colossal elliptical galaxy called Messier Object 87. And in the very core of this galaxy lurks a supermassive black hole with the mass of many million suns. And I just forgot the number right now. I'm going to look it up so I don't get it wrong for you. Yeah, 2,400 billion suns.
Oh my God.
That's the mass of the black hole in the center of this galaxy. 2,400 billion suns. So it is a huge,
That's
huge black hole. Compared to the supermassive black hole in the center of our galaxy, which is just 4 million suns. And so this was the black hole whose accretion disk was imaged for the very first time a couple of years ago by the Event Horizon Telescope. And if you bring up an image of this online, maybe I'll do that for you right now. This black hole emits this incredible X-ray jet out into space. And I'm going to share that with you so you can see it. So we're looking at just the very core of the galaxy in the image that Mike is taking, but there's this incredible X-ray jet
Wow.
that comes out from just outside the event horizon of the black hole. So it's a pretty amazing object. And the images that were taken of it are more along the lines of what you can see here. This is the accretion disk around that black hole.
And wasn't this photographed primarily by a woman, or
Yeah, so the grad student who actually figured out the algorithm,
that's what it
linked
was.
the telescopes together, was a woman astronomer. And speaking of which, Benj, I'm glad you brought that up, because this month is
Oh yeah.
Women's History Month.
Yeah.
And Wyoming Stargazing is honoring 31 great women astronomers in our Instagram daily posts and our Facebook page this month. And the really cool thing is that it was easy to find 31 women astronomers who made significant contributions to the field of astronomy over the past 100 and so years. Many of the names I hadn't heard before, some of which I had, but it's worth learning about the history of all these great female astronomers who really changed the way we understand the universe. So check that out in our Instagram posts and Facebook page if you want to learn
Definitely
about all those incredible astronomers. So stop my share here and just say thanks again for being here. We really appreciate it. And have a great evening, and we hope to see you next time.
Thanks, Mike, and thanks, Sam. This was
Thank you,
wonderful.
Benj.
Thanks
Mike.
for
Sam.
looking.
Great.
Our
Thanks,
pleasure.
Mike.
Thanks for
Thanks,
joining us.
Sam.
Thanks,
Yeah.
Mark.
Thanks, Deb. Thanks for being here. Yeah, Mark, thanks so much for keeping us honest.